All right, so I'll just say it all again. My name's Tovio Roberts. This is another Galvanize Data Science Prep study hall. And if you are just tuning in, then you wouldn't have experienced just watching my lips move while typing stuff into this text editor. So, yeah, let me just back up to this question. Can we go over continuous distribution type questions we might see on the technical interview? It seems like most of the technical interview prep videos are almost all discrete problem sets. And the way I answered that is yes. We can go over some things related to continuous distributions. I don't want to put too much focus on those because we're likely to ask you only conceptual questions about them. And in regards to that, that's going to be normal and exponential. So I have a question up here that looks like something you might see on the technical interview. There are packets that travel through a router at an expected rate of 5,000 per second. Assume that each packet is independent of other packets and that they follow a Poisson distribution in our expectation of how they travel through the router. So yeah. What distribution might you use to model the time between packets received by that router? If you have a suspicion about that, go ahead and put it in the chat, and and we'll kind of just think about this, right? We'll talk about it. And another thing that I might think about is another conceptual question related to continuous distributions. Let's say you measure the height, the height of aspen trees on the side of a mountain in Colorado, which is where I am. The aspens are about to change, and it's gonna be really cool. When I say the height of aspen trees, it's interesting because aspens are actually these massive single organisms, right? And it's just really cool. So we're not assuming that these are separate organisms. I don't know. I don't really need to clarify this, but I just wanted to clarify it because it's kind of a neat thing. I think they're the largest organisms in the world. That's what I keep hearing. I think that's true. But you know what? I'm saying something without, let me just Google this. I'm sorry. It's just me saying things that I should Google before I say. What is the largest organism on the planet? What? Okay, you know what? There's a specific honey fungus measuring 2.4 miles across in the Blue Mountains in Oregon that is probably the largest living organism on Earth. Great. One-upped by a honey fungus. Aspens. Let me just... Wow. Okay, let me just rescind what I said about aspen trees. They're really cool. I'll leave it at that. And a single aspen grove or set of clones is going to all change color at the same time, and then that makes this really amazing patchwork pattern across the mountains. Anyway, you're measuring the height of these aspen trees, and we might ask the question, what distribution would you expect the height of those trees to follow? Okay, so these are the kinds of questions we might ask you on the technical interview. And this first one, somebody threw it in there. This is exponential, right? So the time between Poisson events, we model that with the exponential distribution. Now, when I ask this question, what distribution would you expect? This is not to say that the height of aspen trees follows that distribution. But what would you expect? Let's see if anybody threw an answer in there. So nobody put anything in there yet, but often when we're measuring things, especially things that grow in a steady way, what we tend to find is that those follow a normal distribution, right? So heights of trees in the forest. If you're looking at heights of humans, that tends to follow two normal distributions, right? A bimodal normal distributions, and that's just due to biological hormones, right? But in normal. But in this, when I'm asking what would you expect, this looks like one of those phenomena in the world that we would expect to be normal. And there are certain, I don't know, this is kind of a magical thing about statistics. When I say magical, I don't actually mean magic. I just mean that these things kind of appear a lot, right? Like stars. The example I like to use is like you take photos of the night sky. How many stars do you expect like if you expect a certain number of stars on average, looking at 10,000, 50,000 photos, you start seeing that if you put the count of those stars and measure by the total number of photos, you're going to start you are going to very closely approximate the theoretical Poisson distribution, and that's discrete, right? But it's something that looks like something we can model, right, with a fairly simple formula, or coin flips and binomial, or chips that have a specific failure rate that run in parallel. That looks like binomial as well. And that's really, as far as continuous distributions go, we're not going to ask you to say, give us the probability that an aspen tree, right? Like, here's a question that we're not going to ask you, right? So what is the probability that a chosen aspen tree is less than 14 feet? Like, this is a given the mean and standard deviation of this distribution, you should be able to answer this, but we're not going to ask you that on the technical interview. Okay, it's a nice thing to be able to do. You want to be able to do that. You're going to need to be able to do that in the DSI, but you're going to have a set of review materials from which you build out more of this foundational knowledge. What we really want, what we are really going for in this set of materials on basic prep is, let me just back out to the stats level. We want you to come away with kind of this ground knowledge, and we specifically want you to be able to dig into these discrete distributions and analyze them through dictionaries, right? That's what we're going for, and not just these distributions, but kind of any problem, right? You want to be able to approach analyzing any problem through a dictionary. That can look a lot of different ways, right? That's not necessarily a discrete distribution problem, but we would expect you to be able to leverage a dictionary creatively. So maybe I'll just give an example of that. This is an example that I've done before in a study hall, but I just want to do it again really fast because it's the kind of thing that we just want you to be able to do. We won't do this specific problem in a technical interview, but it's the kind of thing that we'd want you to be able to do. So I'm just going to go to Wikipedia. I'm going to grab a random article, and it's going to be this guy, Bill Ayers. Huh. Okay. And I'm just going to throw it into, throw that into a paragraph. Okay. And that's fine. Okay, so maybe a prompt here would be write a dictionary, write a function that returns a dictionary of word counts from a given paragraph. Little caveats here, like, clean punctuation out of the paragraph, and I think that's good enough. Yeah, I think that's fine. So we've got some special characters here that we might want to think about what to do with. It's going to turn out the way that we clean this. I'll just do it in a very boneheaded way. We won't actually worry about these special characters. All right. So the first thing, if I'm going to write this function, the first thing I'm going to do is just write a cleaning function, and I'll call this clean paragraph, and let's pass in a paragraph. And every time I do this, I do it differently, but I'm just going to do this in a nice, simple, kind of base Python, easy way. So I'm going to omit numbers and any punctuation. And you might notice offhand that this could be a little bit of a problem. For example, here, US, right? Like if we're thinking US, if we eliminate punctuation here, well, you know what? That's not really a problem. Because depending on how we do this, we could include U space S, but that's not actually how, that's not how that'll happen here. Okay, yeah, never mind, sorry. The place where I was thinking there would be an issue is self-described, right? Self-described is different from self and described, right? Like self-described has its own semantic impact in language, whereas self and described separately exist with their own impacts. But we're not going to worry about that. We're going to be just a little naive here, and we'll say A, B, C, D, E, F, G, H, I. Okay, and all I'm going to do here is I'm going to go through this paragraph, just iterate through it, right? So I'm going to say for oh, you know what? We are gonna lose US here, aren't we? No, we won't. Sorry, I keep going back and forth on this. Okay, so for each letter in paragraph, and then I'm going to lowercase the whole thing. So cleaning the paragraph is going to include lowercasing it. I'm going to say if the letter is in alpha, then we are going to, oh, whoops, I want an empty space in here as well. I want to preserve empty spaces, of course. So if the letter is in alpha, then we can just out plus gets the letter, and let's see what this gets us. So we'll return out, and I'm going to just run this. I'll print the clean paragraph of the paragraph and see what we get. And I think that does essentially what we want it to do. Notice we've got this RZ in here. That's something I didn't account for, but it's due to the phonetic alphabet here, where RZ those are valid characters in the alpha that we made. So we included them. Again, I'm not going to worry about it. Let's just leave it as it is and not worry. So this is good enough. during the S Ayers, during the 1960s. So we've got this sort of erroneous S in there as well, and that's okay. You know, this is, if we wanted to make a better cleaning function, we definitely could, but we don't need to at this point. So what am I really trying to make here? I want to write a function that returns a dictionary of word counts. So let's go ahead and do that. So this is going to be a word count dictionary, and we're going to take in some string. We'll just assume that, and that string is it can be dirty, right? It doesn't need to be clean. And we're going to say, so this string modified is going to get clean, what is this? Clean paragraph of the string. So I'll just grab that, of the string. And I'm going to say, we'll take that clean paragraph and we'll just split it as well. So maybe I'll just split it on empty spaces. And let's call this string list. Okay. So we've got the string list. We can just take a look at this offhand and make sure it's what we want. And we can also clear up a couple things in it, right? So I'll just print the result of this. And I think what we'll find in here is there are a few things like the letter S, right? We don't really want that. What else don't we want? We don't want empty spaces. And we've got a couple of those as well. So probably what I'll do is omit the letter S, right, for 1960s or for something apostrophe S. And if you think about anything like that, it's not really meaningful in and of itself. It has some function, but it's not really what we want. So I'm going to go ahead and make a dictionary, and I'm going to say for word in the string list, if word is not equal to an empty string, or I could say if the length of the word is greater than 0, if it's not equal to the empty string and word is not equal to S. I don't know. I don't think there's going to be a meaningful S in there, just offhand. Oh, another thing we might want to consider is that in this case of US, right? US here can be easily conflated with the word us, but that's a different issue that we're not going to deal with. We'll be fine with it. Okay, so word.count. Okay, if the word is not that and not that, then I'm just going to say d sub word. And I'm going to say if the word is not in D already, let's say that as well, then d sub word is going to get the string list dot count of the word. And then we can just return that dictionary. So I'll make this look a little nicer. I'll say for kv in that dot items, and I'm going to do this sorted just so we get it in alphabetical order. Then I'm going to print the k and the v. Right? Same thing that we keep seeing over and over again, this printing pattern for dictionaries. Just an easy way to print dictionaries. Oh, need to make that an F string. Okay. So, so here we've got a word distribution, right? A, activism, also American, and arose at Ayers, Barack. So One thing you might notice offhand is that we have a bunch of words in here that are not contributing to the overall meaning of this in some way. Like for, what does for really tell us? And I would even argue he, his, in, if we were trying to think about this as representative of a chunk of text. There's a lot of things in here that are not necessarily helpful in distinguishing one paragraph or one set of paragraphs from another set of paragraphs. So, and that's fine. That's fine. We can get deeper into this in an analytic way, but maybe what we want to do here is think about each of these words as having a general frequency, okay? And let's say that somehow, and this obviously isn't the case, but let's say that this is somehow representative of a whole chunk of different paragraphs, right? That we would expect some kind of similar, that would give us some sort of sense of, how do I say this? If we think about this paragraph as being representative of a whole bunch of other paragraphs, then we might look at this in terms of the percentage frequency, right? And how would we do that offhand? If somebody has an idea, how would we say, well, if this is representative, then the probability of selecting a word at random and getting in, how would we figure that out, right? And I think this is how you pivot the understanding around these dictionaries. Is, well, we go from counts to probabilities. How do we do that? And I'll let you think about that for a second. And there's a really good question in here. And it's, how about sorting the dictionary according to the values, not keys? Wouldn't that be more informative? Yeah. I think that could be more informative. It's a little bit trickier than you might think, actually. And one of the ways that, let me think about the easiest way to do this without getting too esoteric. How about this? We could unpack this into a list of tuples. And why don't I do that? Yeah, I'll do it like this. All right, so I'm gonna just call this word tups, and I'm gonna make this a list, and I'm going to say, let's do this. Let's do this. So for the key value in the sorted, we don't need this sorted anymore, but yeah, I guess I will take this out. And let's say word tups dot append, and we'll append a tuple of the value with the key, right? And I'm trying to think if there's a nice simpler way to do this that is immediately possible without getting too esoteric. Okay, I mean, this is fine. We'll just do this. So I'll say for VK in sorted of word tups reverse, I believe it's reverse is true, then let's print the key and the value. So I think that does, oh, too many values to unpack, expected to. What am I doing there? Line 41, for KV in word count dot items. That's why. Okay, so that did what we wanted it to. Notice now we're, the most frequently occurring word is the, of, in, and, a. It shouldn't be surprising that those are the most occurring. Yeah, and this is a simple way to solve that. Often you'd solve this a little bit differently, like through let's see. Oh, you could use collections. That's another fairly simple way. And anyway, this is the way I would recommend doing it, because this gives you a clear idea in the base language how to do this. So, all I did was I appended, I just reversed the tuples and appended them to a word tuples list, and then we can just go through the word tuples list, right? And it just requires a bit more code. You can do this at any time without, importing a special operator to do something more detailed. Okay. All right. Yeah, and the question that I had asked earlier, how would you represent the frequency here? Well, yeah, you would just you could take each count and divide it by the total number of words, right? And so how do we get the total number of words? Well, that's the length of d.values, right? So here, probably what I would do is just abstract this out really quick so that we could get that. I would take this and, do that. And I would say for kv and d.items, and I would say maybe I would just do this. Total gets d.values, and then we can get the sum, not the length, but the sum of the values. And I'll call this total words. And here, when we're dividing v, we can just divide that by total words. So let's see if that works. Yeah, and these are our probabilities if we're assuming that this is representative. Yeah, and right when right after I did this, since there's a little bit of lag, right? I think there's like a 20 or 30 second lag. Somebody recommended, in the F string, could you divide the value by the total number of values? Yeah. The word count over a list of values with the list summed? Yeah, exactly. That's exactly what we did here. And so really what we're doing here is we're pivoting what's coming out of this function. I say pivoting, and I don't want to misuse that term. We're manipulating a dictionary in order to get some other information that we might want to see. So, I could abstract this into another function, and why don't I do that? And I'll call it word count probas. Actually, let's do just word probas. And again, we'll just put a string in here, and in this case, we'll call out to word count dictionary, right? And this will be what we start with, and then I can just take whatever we've got going on down here, right? So I'll grab that. So we've got our total words, and then I can just modify D directly since I didn't pass it in. I'm not modifying the parameter. I can just say for key value in D.items, and then I'll just say D sub K. So each key is going to get replaced with V divided by total words. And then I can just return D. And instead of, so here I'm, let's see. Do I still want to do this? No, I don't need to do this at all. So I'll just say D gets this, and this is called paragraph. And I'll say for K, V in D.items, and we'll just print K and V. And that gives us the same exact thing we just got, right? So, you know, this is working under the assumption that we have something that's representative. Now, how might we, I don't know if anybody has any ideas, how could we make this actually give us something representative? Yeah. And this kind of lends itself to, you know, how do you build confidence in a probability? So if we wanted to actually think about Wikipedia in terms of the like if we select a word at random, and we want to get a clear probability of what that, you know, of that word being pterodactyl, right? How would we do that with the most confidence? And while you're thinking about that, let me go back and just say, you know, this is using dictionaries to analyze something. That's all this is, right? And having this familiarity with dictionaries is really important, right? Like you wouldn't be able to do this word count dictionary and these word probas if you didn't feel fairly comfortable with dictionaries. Let me answer a question there. Representative of what? All of Wikipedia? Yeah, yes, all of Wikipedia. And there's an initial answer that I would say is correct. Sample a lot of paragraphs, right? So, you know, first, you might even consider grab all the text of English Wikipedia, right? Like the entirety of the text. Clean it in this fashion. You know, it'll take a while, but you could build, you could essentially build these parameters of the distribution with very, very high confidence. Like, I mean, I guess they'd still be statistics because Wikipedia is going to get modified as you're doing this, but you're basically getting to the point of having parameters. So you could do all of Wikipedia. What would be more practical is, yeah, sample randomly, I don't know, a few 100,000 paragraphs, and then you might think about this. Is your sample representative? Then you could also have another process running on all the text of Wikipedia and see how close your probabilities get. Now, my suspicion is that, okay, like the probability of the word Bernardine is going to be so low that you may register a non-probability there, right? Because of issues with precision, just basic precision issues. But maybe not. Maybe it would just be really, really, really low. You might also need to get use a different data type to be able to represent this effectively. Like there are these data types. Let's see. Big num. Let's see if I can find. Usually in any language you have a concept called big num. And let me see if I can find that. Big num. Big num. No. Bitwise, let's see, large. Usually I can find that kind of stuff really quickly in the Python documentation. But notice, like, for big numbers, we start losing precision way out on the right. In this case, we're getting to all zeros. This looks like it's for well, this might be fine. Yeah, and then we go into Java, where we would use big integer. Okay, you know what? I'll have to do a little research on this. I know I've done it before for large numbers. Arbitrary precision is what we often call this. If you've ever used Ruby, Ruby has this amazing arbitrary precision. But I'm not sure how that is actually implemented in Python. Okay, yeah, I don't want to get too in the weeds here, but essentially what this is doing is it's splitting kind of each side of the number so that you can arbitrarily be precise. This is actually a manual way to handle big numbers in Python, and I just figured there'd be a simple object that you could use. And I don't see anybody talking about that, and this is only a couple years old. Okay, well, why did I start talking about that? Oh, yeah, that's right, because if we're thinking about an arbitrarily, like, if we're thinking about the name Bernardine, I just don't think Bernardine is going to, even better, Dorne. This is likely to not appear that much in Wikipedia, and we may not actually be able to store any value for Dorne. And effectively its probability would be 0. If we actually wanted to represent that, it seems like we'd have to pick apart our float and come up with a scheme to store part of the float in one object and the rest of the float in another object, and just have a split class for that object. That's kind of out of the scope of stuff we would do here. I think it's a cool problem. Maybe I'll stream on that sometime, because depending on what you're doing, like especially if you're doing like certain physics problems, you need some massive numbers. And yeah, I mean, we could try to write something like that from scratch sometime after the technical interview push. Anyway, backing up. This is really just about taking a dictionary, kind of, using multiple lenses on that dictionary, right? So another thing we could do, instead of a word count dictionary, I'm going to write something called a count word dictionary, okay? Where, again, we take in a string. And again, we're going to grab the results of this, right? So just snag this little line, and we're calling up to this word count dictionary. And we're getting this dictionary here. And I'm going to make a second dictionary called dout, or let's say, let's just call it dout. And this time, we're going to have counts as the keys, okay? And so what we'll do is for every word count, we're going to have as a value a list of the words that have that count, right? So I'm going to just say for k, v in d, d.items. And this will be a little this this word probas, right? Or even this where we were able to just count the words. In this case, we'll say if v not in d out, then we'll say d out sub v, right? So I'm just inverting the dictionary in some way. This is going to start off by being an empty list, okay? And then I'm going to say if the key is not in d out, no. Oh, sorry, yeah. D out sub v. If the key is not in d out sub v, then we'll say d out sub v dot append the key. Now that may seem like what am I doing there? Let's just look at the output, and I think it'll be pretty clear what's happening. So this will be I'll just get this, the count word dictionary on the paragraph, and definitely don't need that. And I'm going to say for kv in d.items, and I'm going to sort this. So now we should be able to see a list of from the most frequent to the least frequent words, if I did this correctly. Yeah, and this is a little hard to read, so maybe what I'll do, I should do reverse is true on this. And what I'll do is the key, I'll just do that, and then I'll say for word in v, let's print, and I'll just kind of tab this in. I can also do \T for tab. I'll tab in and I'll print the word. So that might look a little nicer. There we go. A little nicer, still a little clumsy, but why don't I make it just slightly better? Let's do the count. Let's do this, word count of k. And so what we can see here is that the highest word count only has this one letter. Then we've got these other words that are sort of in association, right, by their frequency. And so we can get this sort of easy frequency association based on the word counts, is education, weather, underground. If we wanted to really kind of narrow this in and make it more helpful, we would remove all these stop words. And why don't I do that? I'm just going to say NLTK, list of stop words. I think I did this before. And I will just grab this. These are the words that are so frequently occurring that they tend to not help in discerning texts from each other. So why don't I do, I'll just make this a list. Oh, I don't want it to be a list. I want to split it. So I'll just split on the new line character, and then this will be, let's do .split on new lines, which is \n, and I'll just call this stop words, gets that, and then in my cleaning function, in my, where should I do this? I guess I have to do it here. For word in string list, if the word is not equal to any of those, and I'm just going to put on a new line here, if word not in stop words, then we'll append it in. And since my other functions depend on this, This should be, I'm calling this word count dictionary, but really this has some cleaning functions in it. I'm not really separating my concerns that well here, but that's okay. Now when we look at this, oh, interesting. Us is still in there. I didn't think us would still be in there. This should be US, but apparently us is not in the stop words. I would have thought it would be for this standard list of stop words, but that's okay. It isn't, and that's totally fine. So here we start being able to see, I mean, we can start taking away some meaning from this in this analysis, right? We can start saying, okay, education, weather, underground. Well, if you're familiar with the weather underground, you already have some sense of what this is about. And these have the same frequency, right? Because, or close enough frequency, maybe if we had a larger set of work on this topic, maybe these wouldn't have the same frequency, but they do because we've got only 3 paragraphs here. But, you know, this is education, weather underground. We might discern from this that there's this Professor Ayers, right? This Ayers person who's a professor and in education and was affiliated with the Weather Underground, and that had something to do with, you know, involvement in something, a lead, like this person was maybe a leader, and, you know, I don't know about Ayers offhand. I know a little bit about the Weather Underground, but, you know, this was happening at a university level maybe, you know, don't know what that's about, don't know why December's in there, war, activism, radical, self-described, you know, I don't know, imperialism, bombing, right? We start getting an idea of what, oh, we also kind of see some issues with our text cleaning, like war and Ayers probably shouldn't go together. So we're getting a little bit of, you know, that's something that we'd probably want to account for if we were going to make this better. Yeah, we get a sense of what this is about, right? And it doesn't mean that we know deeply what it's about, but we get a sense of what it's about by this simple, you know, simple manipulation and kind of turning of these dictionaries, right? And that's the kind of thing we want you to be able to use in analysis, right? So I think there's a video in the technical interview playlist on the sigmoid function. And with the sigmoid function, you know what? I think there's associated, there's an associated Jupyter notebook with that. Let me see if I can, let me see if that is listed in this description. I'm gonna do my best to, I'll just mute it so that I don't start blasting us with with audio from here. Yeah. Let's look at this Collab really quick. If you didn't notice in the description for the technical interview lecture playlist, there's a Google Collab that walks through all of the code here. A student put that together, which is super great. I'm really thankful that they did that. It didn't occur to me, you know, didn't occur to me that to even do that, and they just put it together. So if I go down to Sigmoid, here we go. And I'm just gonna snag this code, and I'm assuming this is the same code that, oh, you know, maybe I will also go ahead and pull this code if any of you want to play around with it. I'll just paste this in really quick before I switch to this other bit of code. Yeah. Okay. All right. So let's kind of walk through this, and this is a good code reading is a really good exercise, by the way, going through and kind of trying to understand what's happening here. Let's look at Sigmoid really quick. So I'll say it might be under a logistic function. I'll just say Sigmoid wiki. This is fine. Yeah, this totally works. So the Sigmoid function looks like this. 1 over 1 plus e to the negative x. So f of x is equal to 1 over 1 plus e to the negative x. This function comes in really handy, and you see it in a lot of spaces. I'll just say that. I don't want to get too into it, but we see it as an activation function in neural nets, and we see it in logistic regression. We see it in the outcomes of classification through the logistic curve. If you want to dig more into that, I feel like I think we're going to write some prep materials on that, actually, but it's something I'll probably go over soon. But it's not something you need to know for the technical interview. But it is nice to know about Sigmoid sooner than later, right? So here, we're just implementing the function, right? We return 1 over 1 plus e to the negative x. And then we're analyzing the outputs of this function. And we can look at that. Why don't I go ahead and look at that? Let me make sure nothing else is printing. There we go. So this is really about just considering the outputs of a function at this point. So if we, this is following this curve right here. And let me just make that a bit smaller. Okay, sorry, somebody just asked, it looks like somebody's computer crashed, and they were asking if the stream will be recorded, and I'm just going to say, yes, the stream is being recorded and will be available as soon as we wrap. Okay, just wanted to let them know that. Okay, so we can sort of analyze these outputs, right? And we're going from -10 to 10. That's the inputs I'm using here. I could be more granular, I could go -10, -9.9, -9.8, -9.7, and we could be even more granular with this. That's something that's absolutely possible. And maybe I'll modify this a bit just to show you that. But what we're seeing here is the specific outputs of this function. If we go to -6, right? If we go to -6, the y value is 0.00247, right? We're seeing this very close to 0, right? And when we get to -2, then we're seeing here at, we can see 0.1192 and -1, right? We're starting to get toward 0.5. And we're able to see kind of this growth, or these changes, the s of x here. We can see them numerically, right? Now we can do this with any function, is the thing. I think with Sigmoid it's interesting because Sigmoid itself is interesting, but we can do this with any function, and we can kind of do it with any phenomenon, as we saw with the words we were looking at before. So in this case, the tack that is taken here is creating a threshold. And I think here this threshold is 0.99. And let me just comment this out. If, let's say, yeah, so the first thing we're doing is we're thresholding by the sigmoid. And we're saying if the value that we're seeing here, if this value is above the threshold, then we're setting the key to 1. And otherwise, we're setting the key to 0. So let's kind of look at this. Let's look at these outputs and get a sense of this, right? And again, this is just kind of a practice in code reading. You come across a code, you come across some code, and you go ahead and look at what it's doing, right? And this may not be super helpful offhand, but let's take a look at it. We're either saying that given a certain threshold, we're either saying assign 0, right? Given a certain probability and the threshold, we're either going to assign 0 or we're going to assign 1, right? And in this case, if our threshold is 0.99, then we have to look all the way, let's see, 0.5, and say we're looking at anything somewhere above here, right? And as we can see, it isn't until we get to 5, like an x of 5, that we're seeing, right? So somewhere over here, right? Anything above this is going to be classified as 1. Anything below that is going to be classified as 0. And this is just building a dictionary of the classifications associated with each value that comes through. So that's pretty simple. Don't really need to print that. And then we can represent this another way through the sigmoid counts, right? So given a certain threshold, in this case 99, and I'm just going to snag this and pull it down here. Given a certain threshold, we build this, zeros and ones, and then we can print this where, let's see, for k, v in thresh dict, if v not in d. Let me just see what this is doing. Oh, yeah. And this is just that pivot, right? This is just kind of taking our keys and our values and swapping them, just like we did with the word counts. And we can see what values, what inputs for sigmoid, given that threshold, which inputs will yield a 0 and which inputs would yield a 1. So given this, we can do something. Let me think of a good way to further this idea and analyze it in another way. Yeah, let's do this. So we want, let's say we randomly select numbers in a range from -10 to 10. Okay, so I'm going to start off by here. Let me first grab that a link to that notebook and just put it in the Slack, just so y'all have it. History. There we go. I guess I can just grab this as is. So I'll just say TI follow along practice, and I'll just drop that link. Okay, so I'm just gonna say from random import choice, right? And this is something we expect you to be able to do, from random import choice. I'm going to I'll just leave this sigmoid up. I might grab something from it later. I'm going to select 1,000 numbers between -10 and 10. So maybe I'm going to write a function called select random ints. And you know, Sigmoid doesn't have to take integer values. We could put real numbers in. We could put floats in there and it would be fine. But for this, I'm just going to keep it simple. And let's call this from a low value, right? And let's default this to -10 to a high value and default that to 10 and do a number of samples. And maybe what I'll have this return is a list. So list of ints, and I'll return that. So I'll return the list of ints. And I'm going to say, I'm just going to build a range. It'll be from low to high, and my tendency here is to be inclusive. And then I will say, let me just do it like this. I'll just do, actually I don't need to do that. Nums to choose from, right? So nums to choose, and then I will say, this is a perfect case for comprehension, but I'll go ahead and say for I in range, actually for whatever, for whatever in range num samples, let's go ahead and say list of ints and append, and we'll append the choice, a choice from the nums to choose. And then we should return a list of ints. Num samples here, I have to give this a default value because I've given the others a default value. I tend to explicitly do this, right? And you know, fill in all the things, even if it's the default parameters. So let's print this. This is going to be a big wall of numbers that we'll see in here. And we're assuming this is following a uniform distribution, right? We're not doing anything to you know, skew this distribution in one way or another. So we can do that. We can take this, and we want to process this. So I'll call this sample numbers, and let's think about how to adapt these functions to do what we want to do, which is get us counts for the classifications above, classifications for 1 and classifications for 0, according to the thresholding that we're going to use. So maybe what we want to do, let's think about this. So the Sigmoid dictionary is going to just give us output values, and then the threshold Sigmoid is going to, let's see, takes a Sigmoid dictionary, and we might just want to build something new here, just to make it a little easier. So let's go ahead and get thresholded counts, and what we'll do is we'll pass in a list of samples, and we'll also pass in a threshold, which will default to 0.5. And I'm going to say, I'm going to make a dictionary, and we're going to have ones and zeros, right? And I'm going to say, I'll just do this. So these are the thresholded, where 1 is pass and 0 is fail, right? or predict true, predict false. There's a lot of ways we can think about this. So I'll default both of these to 0. And I'll say if, and we've got this sigmoid up here, if sigmoid of x, right? If sigmoid of x is less than or equal to the threshold, yeah, I'll do less than or equal to. It doesn't really matter here. Oh, it might. Let's do less than the threshold. Then d sub 0 is going to be incremented by 1. Otherwise, d sub 1 is going to be incremented by 1. And of course, we need to do this for every sample, right? So for let's say for x in samples, do this, and we can just return d. All right, so I'm going to say, I'll just do this, get the threshold counts, and we need to take this and move it up because, yeah, I'll just grab this and move it above threshold counts. And maybe I'll put a line in here, right, for the things that are new in this. So get the threshold counts, and we'll pass in some samples, which are here. Maybe I'll just delete that for now. And we'll change this threshold to 0.99. Okay. And what's the last thing I should do here? Well, just for key value in d.items, I could just print. I'll just print d to start. So let's print d. Oh. Key error 0. Well, that makes sense because I made these strings. I really didn't need to. So let's do that. Okay. So in this random process, we can see that 1 came up 278 times and 0 came up 722 times. If we run this again, we're going to see variation, right? And that's fine. Now what we could do, if we were trying to build an expectation, and I think some of you have seen me do this a number of times, we could run this over and over again, and we could settle on some kind of expectation, right? So why don't we do that? Why don't I try to eliminate some of our uncertainty here, and if I'm getting the threshold counts, I can just do this. Well, I'll take these, and let's say samples. Oh, whoops. We want to pass in some samples. I want to do a number of trials, and I'll set that to 1,000. And so now we're getting our sample numbers still. We're still going to do that. And I'm going to build a dictionary from this get thresh counts, right? And threshold is just going to be threshold. Samples is just going to be samples. I'm going to throw that into a dictionary. And then I'm going to make a second dictionary called dout. And that's going to be a dictionary. And num trials times, so I'm going to say for whatever in range num trials, we're going to, oh, sorry, this doesn't need to be here. This needs to be here. We're going to get the thresh counts on those samples, right? So every time we do this, we should be getting different samples, right? We're not getting the same samples every time. And so we should be able to run this over and over again and average the counts, right? We should be able to average these counts, and just grab this, right? We should be able to average these as they change, and if we do this enough times, we're going to see some like convergence on a specific expectation. Okay, so even though we're taking the sampling approach, we can start giving an estimate as to what our expectation is. All right, so for whatever in range the number of trials, I'm going to get this dictionary every time, and I'm going to say, well, you know what I'm going to do here? I'm going to say this is going to be a dictionary that has a key 1 and a key 0, and what I'm going to do here is just make these into lists. And I'm going to say d out sub 0 dot append d sub 0. And I can do the same thing for d sub 1. So unless I'm mistaken here, I'm just going to return d out, and there's a really good question that that I'm going to address in just a second. So we're going to get the threshold counts, and I need to put a colon there. And oh, this should be get threshold counts. I think I was going to call that average. Let's just say that. Is that? Yep, that works. All right. So we're going to go ahead and do that. Num trials 1,000 and threshold 0.99. And this is going to be a little messy, but let's just, that should be average. Samples, samp nums. Okay. So doing something wrong there, obviously, because I am not randomizing this sample nums at all. So I'm going to move this sample nums into the get thresh counts, so that every time we call this, we're actually running this again. And I'll just do this. So samp nums, number of samples from select random ints. Yeah, okay, so I'm gonna just change this to num samples gets 1,000. And this will make more sense. So I'll call this samples, and I also need to put these in here. So all I'm doing is ensuring that these are that this is run over and over again, selecting random ints. The reason why we're getting all these same numbers is that I was using the same list of numbers over and over again, and so this will just get us new randoms every time. All right, so get thresh counts, and let me make sure. Okay, so we can get rid of this number of samp nums, that is, because we don't need that anymore. Get thresh. Now I just need to troubleshoot a little bit. So if we're getting the get thresh counts average. So we get the threshold counts and samples D. I need to pass in these values. So low, high, low, high. We're not passing in the samples because that's being generated every time. And let's see if that gets us something like what we'd expect. And this function's not quite done yet. There's one last thing I'm going to do on it. But let's make sure that we're getting a bunch of different numbers now. Oh, float object cannot be interpreted as an integer. On line 52, let's figure that out. Choice num to choose. Nums to choose range high. Huh. Num samples. Is that why? From low to high. Num samples times. It's 1,000. Line 61. Interesting. Oh, I think I see what's happening. I am trying to put a float value in there when I call this. So select random ints. Let me just track that down. Low, high, num samples. Interesting. It must be when I'm calling get thresh counts. Yep, totally. All right, so this is going to be, I need to put a num samples in here, and I'll set that to 1,000. And I should also be passing that in front of the threshold in order to have that work properly. Yeah, that's where my error was, I think. So let's find out. Yep, there we go. So let's just look at this. There's a lot of variation in these numbers, and that's fine. We've got a key 1. It's hard to see where the key 0 is in here. I'm sure it's somewhere. Not too worried about finding it. But notice these are all the numbers that are, sorry, all the counts of 1 that we're getting. And if we average these, we should have something close to an expectation. And we'll do that presently. So all I have to do here, we have number of trials. All I need to do is say, I'll just take these, and d out sub 0 is going to be divided by the number of samples. And we should get something a lot cleaner down here now. Oh. Oh. Yeah, that's not going to work because we need the I'm silly here. So we need to do the sum of this divided by the length of this. Yeah, unless I'm having a little brain malfunction here. Let's see. No, that looks very reasonable. So here's our output. This isn't going to be super easy to read, but let me. Oh, that's not bad. Okay. So yeah. So here's something like our expectation for the above threshold and the below threshold. And if I run this again, we'll get another value here, right? That is going to be reasonably close. And we could we could run this number of times and perform that same process again. And that's going to, further get us in the direction of what we're looking for. The other thing we can do, there's a great question here. Why wouldn't we just increase the number of samples in the original sampling function to a much larger number? We could. And in fact, let me, get thresh counts, average. Let's increase the number of samples here as well. And let's just make this 2000, and this should be a little bit better even. Oh, what? Oh no, that makes sense. Sorry, I we since we've got since we're dealing with counts, right? We're dealing with an expected number of counts. So this will get us, tighten up our bell just a little bit, but it's really this number of trials that's going to tighten our bell the most. So I'm going to do, this is sort of similar to something called bootstrapping. But really, it's just this is just a sampling approach. Notice here we're settling, right? 285, 714, and we're not traveling as much. Like we've really tightened our bell, and this is a more effective way to tighten the bell in general. So let's change this to 3000, and we're not adding quite as much. I mean, we're adding overhead, but this is our outer loop. If we increase the size of our inner loop, it's still it's similarly like expanding, right? Because we're doing 3000 of 1000. We could do 1000 of 3000. It's really this outer loop that is going to tighten our bell most effectively. But we could do both, and let's just see how that goes. Of course, now we're dealing with expectation that's double what we were dealing with. So it's a little harder to interpret in comparison. So let's bring that back down, and I'll just do 4000. This will take a few seconds to run, but it shouldn't be too bad. Okay, so this kind of looks like it's falling at 286 and 714. I might be wrong about that. It might be 285 point something. It's something that we could analyze to some degree further, but we don't need to. The takeaway here is, we've got this sampling process, right? We're performing a number of trials against a number of samples, and we're sort of narrowing in our belief about an expectation, and that's really what the goal is here. And we see this. We see this in a larger context of reducing uncertainty. And this is just kind of a boneheaded way to reduce uncertainty, or to define our certainty. Cool. Yeah. So again, if we're sort of considering this as an analytic process, right? We've got some function, and we've got multiple ways that we can analyze the performance of this function and the outputs of it. So we've got this sort of closed form, not closed form, but we've got this sort of, we build a range, and then we're looking at the values for each input to the function. And we can perform counts pretty easily, like what is above the range, above the threshold, what's below the threshold. And we can also take this kind of sampling approach in order to gain an idea of expectation of the number of counts of something. So maybe what I'll do is delete, because I don't think we need any of these in order to use this new code. Yeah, I'll do this, and I'll make sure this still runs. And I'll kind of annotate this. So this is kind of an analysis through a sampling approach. Definitely remember from random import choice. Definitely remember from math import E, right? Just simple syntax to remember. Yeah, and let's see. Is there anything novel that I'm doing here? Yeah, here we're just essentially getting expected counts of ones and zeros. Okay, so let me just make sure this is running. Yeah, okay. So I'll go ahead and throw this into the Slack. And I think we could look at one more thing from that notebook that I think can be helpful. It's sort of looking at continuous values. You know what might be better? We might just revisit normal distribution. Let me think about this. There's some code I wrote recently that I think might be nice. Yeah. Now, you know what? I'm going to table that. I was thinking we could... I'll table this for next time. So it would be something like building a normal distribution. Histogram. Building a histogram for the normal distribution. But I think I want to, and taking this kind of sampling approach, right? It's just trying to figure out a nice phenomenon to use to get these normal numbers through a random sampling approach that doesn't just call out to like a NumPy to get normally distributed values. I think it's Okay, I have a nice idea that might just bring this kind of into reality a little bit more. So think about how to do this, and let me define this problem and kind of leave it with you, and we can look at solving this problem next time. This isn't something that you'd have to do for the TI. It's definitely out of scope of that. But let's say you read in an image, And we're going to assume some things about that image. We're going to assume that the pixel values, I'm going to say read in a grayscale image. And I'm going to say assume the pixel values are between 0 and 255. And we might even take that a bit further and say if the pixel vals are between 0 and 1, convert them to the range 0 to 255. You know, just offhand, how would you think to do that, right? If you have values between 0 and 1 and you assume that values between 0 and 1, float values between 0 and 1 can be effectively converted to be between 0 and 255, how would you do that? If you have a quick answer to that, go ahead and post it, but it's actually really simple. So you read in a grayscale image, and you want to so create a dictionary where the keys are bins of, let's say, 10. Okay, so you're going to have essentially 0 to 10, 11 to 20, right, etc. are bins of 10. It's a little bit weird because of 255, because then we've got like the high bin is just sort of off the edge, right? Like if you have a value 253, which is basically white. If you have the value 253, you're kind of you've got a bin of 5. Maybe we could do bins of 5. Would that work? Just to make all the bins the same size. Well, we don't have to worry about that at the moment. So let's just say bins of 10. Our bins of 10, and I'll say with the final bin being 250 to 255, right? So we're just accounting for that, or 251 through 255. No, actually, let's say this: 246 to 255. Effectively, these are all very, very high luminance, so they don't really make a difference. So create a dictionary where the keys are bins of 10, with the final bin being 246 to 255. Count the number of pixels that fall in each number of pixels that have luminance, right? And by luminance, I mean have a numeric value. Count the number of pixels that have luminance, which have a numeric value, that falls in each bin, right? And so what would that look like effectively, right? So we've got something that looks like 0 to 10. And this is a kind of cumbersome key construct, so maybe what we could do is just have this be 10, right? So 10, that's assuming 0 to 10. Yeah. And then, you know, this is a very dark color. This is very close to black. We could say, well, there's 234 pixels, right, that fall into that. And then between 10 and 20, inclusive of 20, that is, then there's, 120 pixels, right? So we can do this. This is something that, given this approach to dictionaries, we can actually do this. It's not that hard. The harder thing about this is, well, first off, a question you might want to answer is, how do you read in an image, right? How do you convert that image to grayscale? Those are probably the key things that you want to consider. One thing about reading in an image is it's probably going to be a NumPy array. And if we want to do this with lists, which is what we'll probably do, we might want to ask how do you traverse a NumPy array as if it's a list? The secret here is that you can just traverse a NumPy array as if it's a list. That's kind of the answer to that question. You can just use it as you can just iterate over it and look at each pixel value. So really, this is the thing, looking for a way to convert an image to grayscale. You can write that function yourself, as it turns out. More likely, you're going to just borrow it from a library somewhere. So yeah, maybe this is a little challenge. I think it's something that many of you are capable of doing, and there are a few different ways to do it. And I think anytime you have a challenge that looks like that, like there are many ways to do the same thing, you get some creativity in it, and I think that can be fun. So I'm going to put this in as a prompt for you if you feel like it. It'll solidify. You know what? Let me change this dictionary a little bit. Let's make it something like this. So the keys are actually strings representing the bin ranges. In that way, you'll have to use f strings, or you should, to do that, to define those bins. And maybe, let's say for an extra challenge here, define, have a parameter that defines your bin width, right? So maybe you want to have a bin width of 25 instead. And so this should be able to change from 0 to 10 to actually 0 to 25, and then 26 to 50, and so on. So yeah, I think that's a nice challenge. Again, how do you read in an image? The question here, the question I'm really asking is, how do you use Google? Because reading in an image is very easy, actually, and you can find out how to do it just by Googling it. How do you traverse a NumPy array as if it's a list? Well, you can just do that. And how do you convert that image to grayscale? That might take a little bit more Googling, or you can find a library that does this very easily. So I'm going to just put this prompt into the thread. And yeah, if you feel like doing it, I think it'll strengthen your understanding of dictionaries. There's all kinds of things that you can do with that dictionary. Yeah, I think it could be fun. So putting that in the Slack. Yeah, I think that's it for me for today. I'll be back Wednesday, same time. That's 4 p.m. Mountain, 3 p.m. Pacific, and 6 p.m. Eastern. We might change that time. We might push it back an hour sometime soon, but for now, it'll stay that time. Yeah, cool. Thanks so much for watching. If you have questions, definitely reach out and enjoy studying, and I'll be interviewing many of you soon.